when you are ready.
All right. Hello, everyone. This is Song Choi, and I'm here with my colleague David Haddad to present you a recent research paper from Kai-Ming He and his research team called Mass Autoencoders are Scalable Visual Learners. And I think this research paper title pretty much explains everything that the paper is all about. And we'll explore the overall idea of the paper and analyze how mass autoencoders are scalable and how they are brought to the computer vision and how they improve over quality of the prediction. So before we jump into the presentation itself and the concept of the mass autoencoders, it will be great to introduce you the main author of this paper, Kai-Ming He. The reason why his name is so familiar is that he wrote a research paper on residual neural networks, deep residual learning for image recognition, to be more precise. Just to give you an overview, ResNet, residual neural networks, an artificial neural network that utilizes skip connections or shortcuts to jump over some layers. So here is the link over here on the bottom, right here. If you have not read the paper just yet, but this time we're not going to talk about the ResNet. I'm just giving you just introduction of the main author of this paper. This time, his research team, Kai-Ming He and al., wrote another paper, which is the main theme of the presentation today, which is mass autoencoders are scalable visual learners. The paper was downloaded on arXiv or ARXIV on December 19, 2021, and published through Facebook Artificial Intelligence Research, which is also known as FAIR. So just to give you a sneak peek preview of the paper, the authors had one motivation in mind, which is masking random patches of the input image and then reconstructing the missing pixels. This is the main theme of the whole research paper, and which makes this paper very interesting to read. So previously I talked to a professor. There will be an agenda for this presentation. So the presentation consists of two parts. So Song Choi, will cover the introduction, related work and approach, and overall the mass autoencoder architecture. And then we'll move on to David to tell you more about the experiments of mass autoencoders and discussion later on. So from now on, I'm going to say MAE instead of mass autoencoders. Is really long term. So every time when you hear the synonym MAE, I'm referring to mass autoencoders. All right, so introduction. So far, we have witnessed an explosion of architectures of continuously growing capability and capacity. So nowadays, you can see highly advanced deep learning approaches to understand how things work around us. So thanks to recent advancement in computer hardware and its improvement in solving more complex problems, the authors assert that they could easily overfit 1 million images and begin to demand hundreds of millions of labeled images. They also stated that this appetite for data has been successfully addressed in NLP, natural language processing, by self-supervised pre-training. We'll talk about that, what self-supervised pre-training later. But what we need to know from this introduction is that hardware advancement, such as CPUs, graphics processing unit from both those companies on the right, made it possible to overfit large-scale images, and self-supervised pre-training has been successful when it comes to understanding the logic in human languages and so on. The solutions, which the authors state, are based on auto-regressive language modeling in GPT and the mass autoencoding in BERT, and those made NLP very successful nowadays. So we'll talk about what those means later on, but this is just preview what we're going to talk about, and this is clearly stated from the research paper. So before we jump into those terminology that I mentioned in the previous slide and why they are so important, we need to first go over two main applications that utilize the power of deep learning. One is computer vision. That's how you see stuff and then understand how things work. And another one is natural language processing. Those are the main applications in deep learning. That's how those machines mimic the way how human beings understand logic, all that kind of stuff. Those two are the main and most powerful applications of deep learning. Why am I saying this? Ever since Google announced BERT in 2020, we have witnessed huge improvement in natural language processing. When I talk in, I don't know, like maybe in English, it can convert to a French, Mandarin Chinese, or Spanish, or so on. And there are two main things research on natural language processing. One is GPT, and another one is BERT, right? They are conceptually similar. They removed some portion of the data and learned to predict the removed content. And the authors state that these methods now enable the training of the generalizable NLP models containing over 100 million parameters. Generalizable means that the model's ability to adapt properly to new or previously unseen data. So drawn from the same distribution as the one used to create the model. So the research on NLP has shown outstanding results. But let's look at the world of computer vision. So I grabbed some sample image of bird. You know, they have the mask and then they tokenize everything and then let the birds to figure it out. That's basically mask autoencoding. But let's look at the idea of the mask autoencoders. It's a form of the general denoising autoencoders. And it is, they are the natural and applicable in computer vision as well. It used to work only, like people believe that it worked only NLP, but it also worked in computer vision based on, according to the research paper. So the authors also highlighted that closely related to research in vision preceding BERT. However, despite significant interest in this idea following the success of BERT, the progress of autoencoding methods in vision lags behind NLP. So there's a limitation between those two. There's a huge gap in between. So after reading the paper, we also realized that the idea of the masked autoencoders was previously come up in computer vision first, but people recognized the outstanding performance only on NLP. Why not? Can we just bring the powerful technology of masked autoencoders back to computer vision? So here is the question that authors are trying to answer. Before we answer this question, which is what makes masked autoencoding different between vision and language, we need to keep in mind that there's three perspectives that make this possible. And it's why we need to understand three perspectives in order to answer this question. So the first one, the authors assert that the architecture used to be different from each other. So in vision, so the image on the right, on the top right, you can see the CNN. Convolutional neural networks were dominant over the last decades. So it has CNNs, usually you show the input image and then have CNN, the neural network to figure out all those image features and then trying to understand all of those. And convolutions operate on regular grids, and it is not straightforward to integrate indicators such as mask tokens or position embeddings into convolutional networks. There's a huge gap in between two. However, there's a solution to it, which is the introduction of vision transformer was able to fill this architectural gap. So it should no longer present as an obstacle. So what they meant was like transforming this case, this is from NLP. Can we just have the mask over here and then hide them and let the machine to predict what that hidden mask will be? And that was possible with the introduction of the vision transformers. Second thing, information density is different between language and vision. So languages are human-generated signals, the way how we communicate with each other, and that are highly semantic and information dense. You need to understand the whole context of people communicating with each other. If we want to train a model to predict only a few missing words in per sentence, this task appears to induce sophisticated language understanding. But images are very kind of different, right? So they are natural signals with heavy spatial redundancy. A missing patch can be recovered from neighboring patches with little high-level understanding of parts, object, and scenes. So if you show us like images with portion of it, you can figure out the rest of the image, how that's gonna look like. So to overcome this difference and encourage learning useful features, the authors demonstrated a simple strategy that works well in computer vision. So masking a very high portion of the random patches. So that's what they're going to achieve in this research paper. And also the authors assert that the strategy largely reduces redundancy and creates a challenging self-supervisory task that requires the holistic understanding beyond low-level image statistics. As we can see, that authors approach this problem similar to how natural language processing researchers would do to tackle the problem. And then we need to keep in mind that the word holistic in understanding is a key terminology here. Okay. And the last perspective is that the autoencoders decoder maps the latent representation back to the input and plays a different role in reconstructing text and images. So the authors give an example of vision. The decoder reconstructs pixels, which would lead to its output to a lower semantic level than common recognition tasks. In language, decoder predicts missing words only, and they contain rich semantic information. However, in BERT, decoder can be trivial, and the decoder design plays a key role in determining semantic level of the learned latent representation. So I just keep repeating the word latent representation. It is a term that is a machine learning technique that attempts to infer latent variables from empirical measurements. So we're going to move on to next slide. So we can safely say that masked autoencoders are BERT for computer vision. So here is overview of the architecture itself. The authors wanted to present a simple and effective and scalable form of the masked autoencoder for visual representation learning. Let's move on to a general idea of this. So like I said previously, researchers wanted to make this architecture as simple as possible. And they also stated that the MAE masked random patches in the pixel space. They have an encoder and decoder design asymmetric, which means that their encoder operates only on visible subset of patches without masked tokens. And their decoder is lightweight and reconstructs the input from the latent representation along with the masked tokens. And this clearly reduces spatial redundancy. Spatial redundancy means elements that are duplicated within the structure, such as pixels in a still image and bit patterns in the file. So here's an example that the research paper provided. On the far left, there was an image has been covered with those patches, those masks, and then it was able to reconstruct that looks very similar to the original image on the far right. So research claimed that this results in large reduction in computation, which makes architecture more efficient. Under this design, a very high masking ratio, about 75%, can achieve a win-win scenario, which is optimizing accuracy by allowing encoder to process only a small portion of patches like 25%, which then leads to reducing over pre-training time by 3 times or more. And this reduces memory consumption, which is very easy for these researchers to scale the MAE to a larger models. So about the MAE, in addition, the researchers claim that the MAE learns very high capacity models that generalize well. Again, generalize means you can predict the data based on unseen data, the previously unseen data. And it is what they wanted to achieve after seeing BERT model, right? With MAE pre-training, they could train data-hungry models like VIT large, VIT huge on ImageNet 1K with improved generalization performance. And we'll see it about those result in part 2, and then we're going to show you several images as a sneak peek before we dive into part 2. So in summary, the research have developed a symmetric encoder and decoder architecture with an encoder that operates only on the visual subset of patches. It is also lightweight decoder that reconstruct original image. Sorry about that. Lightweight decoder that reconstruct original image from the latent representation and masked tokens, and masking a high proportion of the input image, about 75%, and it was non-trivial meaningful supervisory task. And coupling these two design enable training large models efficiently and more effectively. Again, they were able to train speed, improve accuracy, training speed was also outstanding by 3 times or more. Learning high capacity models that generate well and transfer performance in downstream tasks outperform supervised pre-training, and it showed promising result in scaling behavior. And we're going to provide you all those experiment results in later part 2. Here is, we're going to move on to result images. Again, these are testing on ImageNet, 1K, and Coca. We'll explore the approach that researchers made in detail pretty soon. So ImageNet is image database organized according to WordNet hierarchy. So each triplet is showing the result. The one on the far left, those are being masked. And then it says that for each triplet, we show the masked images on the far left. So you can see on the far left, our MAE reconstruction in the middle, and the ground truth on the right. Now, masking ratio was 80%, leaving only 39 out of 196 patches. That means they divided these original images into 196 different pieces, which they call it patches. And they left only 39 of them and then have this MAE to reconstruct that image. And surprisingly, they were able to reconstruct in very high detail, as you can see from this. And they tested on ImageNet, which is open source image database according to ordinal hierarchy. And then you can see that you showed pretty good result here. Moving on to next, the COCO. They tested on COCO validation images. COCO is a large scale object detection and segmentation and caching data set. It's also the open source. The example result on COCO validation images using MAE trained on ImageNet. Again, they use ImageNet and they could observe reconstruction, which they reconstructed pretty well on this one too. Following up, reconstruction ImageNet validation is using MAE pre-training, masking ratio of 75%, but wide input and higher masking ratios. That means they covered all images. They divide into many different pieces, and they cover 75%, 85%, 95% of the original images, and they were able to reconstruct image 75% like in a higher detail, and the rest, as you can see, like they're like, for instance, 3 zebras here, and then they're able to reconstruct quite well. Less blurry on the 75%, and there's only 1 zebra in drinking water. With your mask only 95%. So let's move on to related work that researchers actually considered. And I think I already mentioned several of them in the very beginning of this presentation. Auto-regressive models that takes previous prediction to generate new prediction. The research did the format denoising autoencoding, but different from classical DAE. DAE means denoising autoencoding in numerous ways. The BERT and the GPT, I previously talked about it, so I'm not going to repeat it myself. And they mentioned that those approach, they scaled excellently and generalized pretty well. So they wanted to have something similar like how BERT did in natural language processing on computer vision. Again, autoencoding is a classical method for learning representations. It has encoder and decoder, and it has latent representation that kind of connects in between encoder and decoder. And they gave an example, APCA and K-means also part of the autoencoders, and they also repeated denoising autoencoders, which is corrupting an input a signal and learn to reconstruct the original and uncorrupted signal. And there are other series of methodology how we can utilize autoencoding, which is masking pixels or removing color channels, like maybe black and white, I don't know. So they utilize the format denoising autoencoding, but they stated that it's quite different from classical denoising autoencoders in numerous ways. Also, mask image encoding. They learn representation from image corrupted by masking. So again, representation is based on empirical, based on experience, and then you figure out what it is. And there's contents encoding paints large missing region using convolutional networks. They gave an example of some research paper they tried using context encoder. Another example they gave us is IGPT based on sequence pixels and predicts unknown pixels. So in this case, unknowns is quite different. Mask patches of image, and through autoencoding predict mask patches. So that's what they wanted to achieve here. Self-supervised learning obtains supervisory signals from the data itself. It learns from unlabeled sample data, it can be regarded as intermediate between supervised and unsupervised learning. So here's an example of self-supervised learning workflow. So they give us label data, and then they learn from unlabeled data and so on. Here's just example that we found together. So we're going to move on to the approach. And just keep repeating myself again, the researchers wanted to have a simple autoencoding approach that reconstruct the original signal given its partial observation. So they covered 75% of them based on 25%, and they wanted to have this autoencoder to reconstruct the somewhat original image. Just like all autoencoders, their approach has an encoder that maps the observed signal to a latent representation and a decoder that reconstructs original signal from the latent representation. They mentioned the one difference is that they adopted a symmetric design that allows an encoder to operate only on partial observed signal without masked tokens, and a lightweight decoder that reconstruct full signal from the latent representation and masked tokens. Masking, what they did is divide the image into regular non-overlapping patches, and then they sample, which they call a random sample in this case, and then they sample subset of patches and mask them, the remaining ones, and then sample random patches without replacement, and then random sampling with higher masking ratio, the ratio of removed patches largely eliminates redundancy, and then creating a task that cannot be easily solved by this exploration of from visible neighboring patches. And then they say it prevents potential center bias. So here is just overview of the vision transformers. So encoder and a decoder, those are all transformers. So what transformers is all about is that in this case, vision transformers, what we are familiar with is the one inside the bird. So you have the sample image over here, and it's divided into 16 pieces, which they call as a patch. And then you place them linearly as an input for transfer encoder, and they had positioning embedding, which means you need to know the location of each image. So it's aligned linearly as an input for transfer encoder, and then have the encoder to figure it out what those are based on those flat patches over here, and then it predicts what those are, and then classify whether this is wood or asphalt and so on. And he would say this is a game changer because he deploys CNN with transformers. So usually people go with the CNN in terms of for images, but now you can utilize the transformers, and then you can have more data with fewer costs to pre-train. And this has overcame the limitation self-attention in vision tasks as well. So MAE encoder, so they said what they did was similar to VIT, the one that I talked about in his previous slide, but they apply only on visual unmasked patches. So in this case, the one that's covered the mask over here, they did not apply VIT on here. They only applied only on the visual ones on here, the one that's not masked. And then the encoder only operates on a small subset, it's 25% of the full set. So this is probably 25% of the whole, the full set of those patches, those pieces. And the mask patches are removed, and they only care about those that are not masked, and they put that inside the encoder, and allowing to train very large encoder with this only fractional compute, right? So that goes inside the encoder. For the decoder, the input to the MIE decoder is a full set of tokens consisting of encoded visual patches and mask tokens. So each mask token is a shared and learned vector that indicates the presence of missing patches to be predicted. And then they added position embedding, just like how the VIT transform is like. They added positional embeddings to locate which patch, which image that belongs to the original input. And without this, mask token would have no information about their location in the original image. And then decoder has another series of transformer blocks. MAE decoder is only used during the pre-training to perform image reconstruction tasks. Only the encoder is used to produce image presentations for recognition. Therefore, the decoder architecture can be flexibly designed in a manner that is independent of the encoder design. And then they experiment with the very small decoders, narrower and shallower than encoder, and so on. So for example, they tried with the default decoder that has 10% computation per token and the encoder. And with this asymmetrical design, a full set of tokens only processed by the lightweight decoder, which significantly reduces pre-training time. I think that's quite outstanding in this case. We're now going to move on to the reconstruction target. So MAE reconstructs the input by predicting the pixel values for each mask patch. So each element in the decoder's output is a vector pixel values representing the patch. And then the last layer of the decoder is a linear projection whose number of output channels equals the number of pixel values in the patch. So the number of, after decoder, this vector is equal to the number of the patches in the target. The decoder output is reshaped to form the constant image, and their loss function is computes the mean squared error, MSE, between reconstructed and original images in the pixel space. So that is similar to BERT, and they compute loss only on mask patches. So simple implementation, the author also mentioned that MAE pre-training can be implemented efficiently and does not require any specialized sparse operations. First thing they did was they generated a token for every input patch, and then they randomly shuffled the list of tokens and removed the last portion of the list, and based on the masking ratio. So if it's 75% or 85%, 95%, and this process produces a small subset of tokens for the encoder and equivalent to sampling patches without placement. So after encoding, they appended the list of mask tokens to the list of encoding patches and unshuffled this full list, which is inverting the random shuffle operation. And then they align all tokens with their targets, and decoders applied to this full list with position embedding added so that they know which location those patches which originally located, so they know where it belongs to. So the masking ratio itself here is figure 5. They're showing the masking ratio. High masking ratio 75% works well for both fine-tuning on the top and linear probing on the bottom. David will tell you more about fine-tuning and linear probing later on. But as you can see, the one on the top, the masking ratio, the 75% showed 84.9%. Well, that was a 6% of 85, but if you compare both of them, that has highest masking ratio. Masking ratio has, like on this line, oops, sorry about that. On this line, 84.9% on the top, and the 73.5% on the bottom. And they tested on ImageNet 1K validation accuracy, and then those two show the best result when the masking ratio was 75%. So we'll now move on to David to tell you the second part of this presentation. David, stage is yours.
Yeah, let me share my screen. All right, thanks, Sangwoo, for recapping the paper and all the background information needed. Can you guys hear me and see everything okay before I start?
Yep.
Okay, perfect. All right, so we have a quiz time for you guys. We're gonna make it a bit more interactive. We wanna see what you guys have learned so far, what you've read and understood from the paper so far, and recap what Sangwoo's gone over so far. So feel free to throw your answers inside of the chat. On the first question, let's just start with the first answer for the first question. What is the difference between the inputs for the encoder and the decoder? So the bread and butter of this paper mentioned something huge about what goes into the encoder versus what goes into the decoder. And what is that main difference that you guys remember reading about or hearing about?
For the input to the encoder, I think the mask samples are not being fed. Whereas for the decoder's input, we are feeding mask inputs also.
Perfect. Yeah. And I see a bunch of good answers in the chat. I see that inputs of the encoder are only 15% of the segments I think it's actually 25%. Input is unmasked image, output is masked image. Yeah, you guys are on the right track. Second question, what percentage of the image is masked for the model? So when we're talking about this input image at the very beginning, what percentage did Songwoo mention to be the main mask ratio? Perfect. And we'll go over why the number in the chat, 75%, is correct, and why they use it in the paper. There's a reason why they just, specifically chose 75. Will we be graded for this quiz? You'll never know till the end of the class, will you? All right, third question. What type of masking is mainly used in this paper? All right, Ginny, he's on top of it.
Random.
There you go. You guys are on top of it. I don't know why we're explaining it to you guys. I'm just kidding. Yeah, awesome. So I'm going to recap for some of you guys and just see where we are. So this is the May architecture. This whole paper has been about the May architecture, and the whole idea of why this paper exists or what they're trying to accomplish is they're trying to use a set of pixels or patches from an image to pass into the architecture and then reconstruct that original image. So as you can see, you have only a few small percentage of the images, so 25%, going into the encoder, going into that architecture and being fed into that final reconstructed target output. So this original image, we do 75% masking, and random masking is used because it was one of the best performing masking ratios, and we'll kind of go over the graph on why. So what they do is they have an original image, they mask 75% of this image after they've patched it up. All these little gray boxes are going to be the masks, as to call them. What we feed into the encoder is going to be those unmasked patches. So only the ones that are not gray boxes are being fed into this encoder. And the whole point of only feeding 25% is where this architecture kind of rises and shines, because now you're using less computation and takes less time to train, and it uses less memory. And this whole architecture is asymmetric, like Songwoo said, where the encoder takes 25% of the data and the decoder takes the whole set of patches, whether they're masked or unmasked. And you can see the difference. What goes into the encoder, so the number of patches coming in, you can think of each patch being a vector, goes into the encoder, and then the encoder outputs the same number of vectors or patches into its output. And the whole point of passing it into this encoder transformer, vision transformer, is to get the semantics of those patches. We want to understand what those images mean and then feed that into the decoder. And they do that by adding the masked images and feeding into the decoder. So there's a little difference in their architecture, but mainly they're both using vision transformers that have been adapted. What else? Okay. They also have positional embeddings, like Songwoo mentioned before. Positional embeddings we'll talk about again. So a question would arise, okay, say you feed 25% of those little patches, those images, how do you know where they belong in the original image? So say you're feeding this patch right here. How do you know this belongs in the top right corner? That's the head of the flamingo. You don't know that. You don't know that at the beginning. And that's why in this architecture, they use this thing called positional embeddings, and they concatenate that in the vision transformer to understand where each of those patches belongs to in the original image. And that's it on the summary. So let's go into some ImageNet experiments. We'll go over what they've done, what they've tried, what worked, what's why they've tried certain things and whatnot. So taking a step back, the whole point of why they ended up using vision transformers comes from the original idea of not necessarily sequence to sequence modeling, but it comes from NLP, trying to understand the context of certain words in the sense of NLP. So if you take a look at this example, this is an RNN-based sequence to sequence model. So say you want to translate one phrase from, in this case, it's German. You want to translate that to English, right? So they use this thing where this entire model is basically a bunch of RNNs. The encoder is a bunch of RNNs and recurrent neural networks. And the decoder is a bunch of RNNs. And it starts off with the first word being passed into the first encoder, gets the semantics, pushes it sequentially into the next encoder, goes on up until it's understood the entire context of this German phrase. And that's being passed into the decoder to then convert that to English. So the issue with that approach in NLP is that one of the big problems of having that is mainly because the context gets lost. So when you're talking about huge phrases, say you have like an entire paragraph or an essay, right? And you pass that into this model, the problem with that is going to lose that historical background or context of the words. And the other thing is it doesn't do things in parallel. And the main reason why that can't do it is because it's sequential. You're passing one thing into one encoder, going into the next, going to the next, all the way down the line. So you can't really parallelize this work, at least for sequence-to-sequence modeling. And this is why we come to the idea of transformers. So we're not going to go into too much detail into transformers, but this paper adopts the idea of transformers so it can understand how to encode and decode something and being able to tackle those challenges that we just talked about. The challenge of losing long-range dependencies, being able to take something big and keeping that contextual understanding of the semantics and coming up with a prediction. So over here, you can see an encoder, and then there's just the decoder and the transformer. Okay, so in this project, again, they use vision transformers as the baseline for this entire project. So you can go ahead and read transformers for image recognition at scale, 16 by 16 words. This is where you can find a lot of the details on this specific vision transformer paper. But the idea that this paper shows is that vision transformers have become more competing in the computer vision world compared to CNNs. So typically we use CNNs, and in NLP we use transformers, but they're able to find a way to use vision transformers for image classification tasks, and then they can apply those sequences on image patches. And this project is mainly the image patches and trying to predict that reconstructed final image. And the benefit of using a vision transformer is that it uses less computation, takes less time to train, and uses less memory compared to some state-of-the-art CNN models. So let's take a look at this architecture. Sangwoo kind of went briefly into it as well. So the vision transformer, originally, what you have is an image. So this image is broken up into patches. It's a 3 by 3 image. And each patch you can consider as a vector. And this vector is going to be fed into this linear projection of flattened patches. And you need to remember again that these image patches have no understanding of where they are in the original image. All they are is a piece of patch in the image. Okay. Yeah, so what happens is that you can consider the linear projection as a matrix. So you're multiplying each vector or each patch by this matrix, linear projection matrix. And what's happening is that you're appending this thing called position embedding. And this position embedding is telling you where this patch belongs to in the original image. And then that's being fed into the transformer encoder, and that's able to predict your final, make the final prediction pretty much. And this is where we kind of utilize that same model and tweak it for our May architecture. But this is kind of like the idea of what VIT large is. And comparing what they've done from the original VIT, they did the same thing. They've adopted positional embeddings that we just talked about to both the encoder and the decoder. So the encoder is a vision transformer and the decoder is a vision transformer. And each of them has a positional embedding. They don't use this thing called relative position or layer scaling as compared to the standard VIT. Also, the main architecture and pre-training, they use this auxiliary dummy token to encode the input. And apparently it doesn't really make a huge difference because they still are able to use average pooling instead of that token to get similar results. All right, let's move on to the next slide. So these are the default settings in pre-training. Just going to kind of briefly go over them and then get into the results. So originally for the experiments, they don't use color jittering at all for the image inputs and pre-training. The reason why is because when they use color jittering, they were getting inconsistent and bad results. So they just avoided color jittering altogether. And then they avoided using drop path and gradient clip altogether as well. Fine tuning. So they do a lot of fine tuning in this in the experiments in this project, in this paper. And just to kind of recollect what fine tuning is. So the idea of fine tuning comes from transfer learning. So if you want to use your model for different tasks, you go ahead and train that model on different data sets and tune it, change the parameters and change certain parts of the model in order for it to perform that new task you want it to do. So say originally you wanted to train this model to take in pixels of cats and dog images to predict a final image of cats and dogs. And maybe now you want to do it on flowers. So what you do is train it on a different data set, and then you tweak some of the parameters, fine tune them, and then you're able to accurately predict those new tasks. Another thing you'll hear a lot is linear probing. So linear probing, you can think of it as just a way of dealing with collisions or keys that map to the same index in a hash table. So in the embedded space, they have this logic that happens, and linear probing kind of tackles it using a hash function to find the index for a key and kind of replacing that key accordingly. So it's just a way of dealing with that embedding space, and that's just what linear probing is in general. Default setting for end-to-end fine-tuning, they use the same thing as VIT, like out of the box. So those, again, are really irrelevant in this presentation itself, but if you were to recreate it, those are the default settings they used. And linear probing, they actually do something different for the MAE architecture. They disable common regularization, such as mix-up, cut mix, drop path, and again, color jittering. They remove color jittering for everything. And this time, weighted decay is set to 0. So those are the settings they use for the MAE. They've taken a few things and changed them. They've tuned them specifically for the task they need. So this MAE architecture has been trained. All of these have been trained, self-supervised pre-training is done on them. Originally, you can see this out of the box VIT original accuracy that's happening on self-supervised pre-training. Then they have their own implementation of the VIT, so they've fine-tuned it. And then there's a baseline, their MAE bread and butter architecture. They've trained this on ImageNet 1K. All of these have been tested on the same data set. All of them have had fine-tuning and linear probing applied to them. And what they're reporting here is the top one validation accuracy for a 224 by 224 single crop image. So you can see that MAE performs pretty much the best between those three. But again, that is not enough to go ahead and say, hey, this is the best one in all these cases. So we do have to look at different benchmarks to make that decision. They go over this thing called masking ratios. So someone kind of talked about this as well, but we wanted to figure out, I wanted to explain to you guys how they came up with the 75% masking ratio. So originally they break the image into patches and then they mask them. How did they come up with 75? So what they did is they tested it on all these different types of masking ratios, starting from 10 to 90% masking ratio of the original images, training images. And for fine tuning, when fine tuning was applied, you can see that when there was a 40% masking ratio up until 80, there wasn't a huge bump in that accuracy increase. Whereas in linear probing, you always saw this increase of accuracy up until the 75% masking ratio. So what they did is they just took the best of both fine tuning and linear probing validation accuracy. And they're like, okay, this worked for both. So we're going to take 75% masking ratio and we're going to apply it for all the experiments because it performed best. So that's why and how they came up with 75% masking ratios. Funny thing is that in BERT, it's pretty much the opposite of BERT. Typically BERT, they use a masking ratio of around 15%. And in computer vision, they typically use 20 to 50%, according to the related works that they've talked about. So it's interesting how this turned out to be 75% masking ratio. It's insane that you have only a few pixels and it's able to reconstruct it off of 25% of the original image. All right, let's talk a little bit about the decoder. So they've applied fine-tuning and linear probing again, and they've tested the changes they've done on the decoder as part of the experiment. So over here you see blocks. So blocks represent the number of blocks in the transformer that they use. So they start off by using 1 block, 2, 4, 8, and 12. And then they measure the accuracy between all these changes they made. So you can see that linear probing has an increase of accuracy as you add more blocks, and it kind of saturates around 8 blocks. But fine-tuning, when the model is fine-tuned, it doesn't really have an effect of adding more blocks in the transformers for the decoder doesn't affect anything to the accuracy. And that's mainly because inside of the, when you fine tune the model, you can go back into the encoder and you can add a few adjustments, adapt those last layers of the encoder to work from recognition tasks. You can't do that for linear probing, but if you go back and change the encoder a little bit, you can make it work for fine tuning to increase accuracy. So that's why you don't really see a huge difference whether you change something in the decoder or not. And it happens the same thing happens when you have different dimensions being tested. So again, they chose 8 blocks for the encoder, for the decoder transformer, because it's just the best accuracy for both fine tuning and linear probing. And the same thing applies for the dimensions. You can see fine tuning again is not very, it's not affected by this change, but linear probing is by adding more dimensions. So the solution for fine tuning is you can go back to encoding the encoder. All right, let's move on to mask tokens. So we mentioned at the beginning that in this paper, the architecture, they feed the encoder 25% of unmasked images, patches, I mean. And the reason why they've tried both. So they've tested both just to kind of confirm that they've done that. And the best result happened to be that whenever they don't add so the encoder, when they pass it an unmasked set of patches, it performed better than when you pass it masked patches. So that is also why they were like, hey, we don't need to do that. So let's keep all of the input patches into the encoder, which are 25% of the original patches. They're being fed in, and then it happens to be that without masking is just better. So they kept it that way, and it's faster. They've tested it out on different encoders. So they've changed the depth, the number of blocks in the decoders, and turns out that with those different blocks, you have a different speed up. So originally, you can take a look at this gray row. This gray row shows when they've tested the encoder VIT with mask tokens or mask patches being fed into the encoder. And from there, they've fed in the encoder with non-masked patches. So everything is from the original image. And it turns out that it's faster and it's also more accurate. And same applies with VITH, large and the H models. So this kind of further verifies that we don't need to pass in any masked patches into the encoder. It works better and it's faster to just pass it the original tokens, patches. All right, so reconstruction target, moving on to that section. So they've tried 3 things. So when they're reconstructing pixels without normalization, with normalization, they've compared it to PCA. Over here, they use 96 for the coefficients, for the PCA coefficients. And the last thing they use is DVAE token. And DVAE is a large convolutional network. And it has 40% of the floating point operations as compared to the vision transformer large. And an interesting thing is that, first of all, they have this CNN compared to this MAE vision transformer approach. You have to add, potentially you have to add more data to it, and it might take an extra step for pre-training, and it still performs worse than your typical MAE vision transformer approach. So that's competing pretty much with CNN and showing you that vision transformers, could potentially outperform other CNNs as well. But in this case, it does outperform DVAE. So they ended up using pixel reconstruction target, reconstructs a pixel of an image of pixels without using normalization. And that performed the best accuracy. So they also test this thing called data augmentation. Data augmentation is changing the data, creating data that hasn't existed before. So you increase your data set in order to train your model on different things. So one way to do that is by cropping the original data set. So images, you can crop certain parts of the image. You can do horizontal flipping, you rotate the image, you change it up, and that creates a new data set, thus being referred to as data augmentation. And they test that to see if the model performs better when you add more data, or a diversity of data, as to say. So interesting thing is that regardless of what they do, having no data augmentation, the original data set, it performs pretty decently, at least for fine tuning. Linear probing, not as much, but when they do fixed sized cropping, pretty much they try cropping for all of these data augmentation. They've also tried color jittering only for this experiment. For the rest of the experiments, they don't use color jittering. Turns out that random sizing certain images and cropping them has the best result. So kind of just like taking a step back, everything I've been showing you leads to how they've built their default settings for the MAE, and why they chose specific features and how they trained it a specific way at the end. They've tried all these different approaches, and everything I pointed out is pretty much why they ended up choosing them. Interesting thing here is we tried 3 different sampling, or not us, the paper tries 3 different sampling methods, technically 4, but 3 different approaches. So we said that we randomly masked the image. And I remember asking you guys that question, what is the percentage and what type of masking? So they ended up choosing 75% masking ratio because they've tested all the different ratios. And it turns out that for linear probing and fine tuning, 75% was the best. But why did they use random sampling, random mask sampling? Well, if you take a look at all these different approaches, right, they have this thing called blockwise masking, and they have gridwise sampling. Originally, what blockwise sampling means is that they take a chunk and they mask a chunk of the image. That's actually taking more blocks out. There's a huge training loss, as you can see. And you also have, it's a bit harder to do than random sampling. Just taking a big chunk and removing it is a bit harder. So you can see this reconstructed image being blurrier compared to the other 2. They also tried gridwise sampling. Gridwise sampling means that you keep every 4 like patches, and the rest you pretty much mask it. You set them all to be gray, so you can see that it's a grid pretty much of masked pixels, and that produces a sharper reconstructed image compared to random. So if you take a look at the accuracy scores, they've tried random masking, which we just talked about. block masking. So they tried it with a 50% ratio. So they take 50% of the image and they block it out, 75% of the image and they block it out. And then they have the grid 75% masking ratio. And the best performing one was 75% random masking. And that's why they used it for the rest of the experiments. And that's why we're like, oh, they use 75% random masking. It's because it performed best. So they stuck with it. So training schedules, originally they pre-trained the models on 800 epochs, but now they wanted to try different epoch lengths, and they wanted to see which ones performed better. If you take a look, these are for the May self-supervised pre-training, and you can see that over time, training the longer you train the model, the better, whether it's fine-tuned or linear probing. And the case doesn't actually apply for other models like I think it's called Moco or Coco or something, but that one actually saturates around 300 epochs. So this kind of is like proof that MAE architecture just keeps on getting better and better the longer you train it, unlike other ones. This is a comparison we can take a look at. The Moco, Dino, and Bait. They all have self-supervised training methods, and the May turns out to be the highest accuracy, trained on all of these different types of vision transformers. And this is just another way of visualizing the different parameters and the accuracy when you have more parameters. And then the MAE is actually second to best. Supervised JFT does better. But for the most part, we've been seeing MAE being one of the top performing architectures from the ones they've compared it to. So we also do this thing called partial fine tuning. The paper does this thing called partial fine tuning, which means that I didn't write it down. It's fine. So partial fine tuning means that they freeze some of the layers and they fine tune the last few layers or other layers, and then they test it out. The reason why is because in linear probing, as it's called linear, it's not really good at figuring out extracting the features, I think, from non-linear classes. So to kind of test for it, they do this thing called partial fine tuning. Again, it freezes some layers and then it lets the other layers be fine-tuned, and then they test it out. And what's interesting is that May saturates around 4 blocks when you have only 4 blocks that are fine-tuned, and anything that they add kind of saturates, whereas the Moco keeps getting better. I mean, it's still not as high in terms of accuracy, but it keeps on improving the more blocks you fine-tune. So I found that interesting as a comparison. And they also do some transfer learning experiments. Through these transfer learning experiments, they've tried, oh, my bad. They've tried object detection and segmentation. Just gonna briefly go through that. You can see that MAE performed the best compared to the rest, but it's on par with the Bait VIT vision transformer large when it's being done on Bait. They've done semantic segmentation. They've also outperformed the other ones. And classification tasks. These are done basically, they've tested the different vision transformers on different data sets just to see which ones perform better. And vision transformer huge 448 performs the best on any given data set that's tested over here. Then pixel and tokens. I'm just gonna, yeah, this part's not, we kind of went through that, talk about the different ones. All right, so let's summarize everything we've talked about. This architecture again takes in a few pixels, reconstruct it into the original image, and it does it efficiently because the encoder has a secret sauce where it only takes 25% unmasked patches, and the decoder takes all of them. So that 25% of the original patches decreases the amount of time it takes to train, and the amount of memory. So you can upscale this entire model and you can test it out, which is the whole point of this paper. The decoder is also lightweight, reconstructs the input from the latent representation along with the mask tokens. And the reconstruction target is again the original image. And the whole point of this paper is that it's faster than your typical CNN in this specific classification task and takes less memory. All right, so discussion, I'm gonna leave it up to Songwoo and I. We're gonna make this more of a like a tag team. So actually, we can do two ways. In the chat, guys, can you guys write down what you think the strengths are for this paper? I know you guys have had to finish your summaries, so I'm curious what you guys think the strengths of these papers are, or this specific paper, before kind of going through that section. Or you can say them out loud.
Gabe mentioned that it's efficient, not computing over mass tokens, and Mohammed mentioned that the downstream task, you can use this for downstream task. I think both of them are the great strengths in this research paper. What else? Do you have anything else you want to add to this? You can talk, you can unmute yourself, you can talk, or you can just write down what do you think the strengths or weaknesses for those papers. Yeah.
Okay. Yeah, no, I think we got.
Yeah,
okay.
I find something very interesting is the random strategy on the mask, and amazing is just random things can still have a very good performance, even better than every 4 patches to be masked, right? And yeah, that part is, but I'm a little bit confused. Is like, how could that, I mean, random be that best option? Is it paper just pick up like for example, like run the experiment 10 times and then one of the 10 for the random result get a very good result and then just show in the paper, and the rest of the 9 times are, you know, just average or very bad. And yeah, that's, I'm curious and want to know, because sometimes when we write the paper, we just want to present the best side of the design, right? But still, yeah, I did not expect the random strategy could do the best. How do you feel about that?
For me, I felt like the most interesting part is when they got to 75% random masking. Like how is that more efficient, you know, than having more images to train on or more patches to train on? That was in a way very surprising that it hit 75% compared to other computer vision models. But one thing I did notice in this paper is that they didn't really write a lot of limitations. So not sure how many of you guys have been able to talk about the weaknesses, which we'll kind of mention as well. But typically papers write, you know, pros and cons or what their paper should be able to, or where the limitation is, where does it stop? And these guys kind of always kept it positive that all these tests, they're doing really good. So I'm curious if you guys have noticed that in this paper as well.
I found one interesting thing here. Like in the graph that they've shown, when the masking ratio is around 50% to 75%, their accuracy is somewhere around 84% or something.
Yeah, you're talking about.
And yeah, this one, yeah, the next one.
This one.
There is a graph. Yeah, this one. And if like at 20% and 10% is 83.2%. I mean, like that means the lesser the masking, the lesser the accuracy. I mean, I didn't understand this part. Maybe I felt it's like a defect or something. Can you explain that? Why?
Yeah, I'll explain that. So that specific test, what they did is so you saw 10 through 90, right, on the x-axis. And
Yeah.
what they did is they started with the original image. They masked
Mm,
10% of the pixels. So only 10% of this image, they added like, say, gray boxes, only for 10% of these pixels, these
yes,
patches.
yeah,
So
I
they
got
tested it.
that, but
Okay.
but why is it like if at all there is masking only for 10%, isn't it supposed to do better than the 50% masking?
I
I delete. Go ahead.
Yeah, sorry, I'm just guessing because I also have this curious. I'm guessing the valid mask and just show here, like here the flamingo, this bird, and in this image only maybe, let me see, maybe 80% of this in the target we can see. This mask are showing this is a bird, and the background they are all dark color, and those are, we can consider they are not valid mask or patches, and that's why sometimes if the random selects the invalid mask or invalid squares, then the result will not be so good because they predict and learn pre-train on these unvalid squares. And when the random select this, the bird flamingos, these squares about these birds, and then it can learn from them. That's why, because always the image cannot be 100% to, present the items or object in these squares. I guess just what I'm guessing. So
That makes sense. Thank you.
That's one thing. And I think the other thing is for some reason, it's able to have a better understanding of the semantics when there's less. That's an interesting topic to throw back at you guys. It's like, why do you guys think it understands better with less patches than it does with more patches in this case, right? Because in the encoder, you're feeding it, say 25%, right? Before, if you want to make this a heavier model, what you do is you feed the encoder and the decoder the entire number of patches. What they do here is they do 25%. So Naveen in the chat said the model is able to learn better latent representation of data, it seems, with more masking. Correct. Yes, that's pretty much what the experiments was allotting to, right? The more you mask the image, the better it's able to reconstruct it. Okay, before we continue the discussion though, we talked about the strengths of this paper, right? Or the main points that they try to bring up. What do you guys think would be the weaknesses, the limitations of using this approach? You can throw them in chat or as well have a little discussion about it.
I felt like sometimes the images are blurry than they should be. I don't know, maybe.
Okay. No, that's a good start. We'll discuss why it could potentially do that.
And the second one is what I mentioned like earlier. It's like 10% is doing 10% masking is doing worse than 50% masking. That's, I thought, I don't know whether it's a good thing or bad thing, but yeah, I felt that was a weakness, but yeah.
Okay. So, okay. So you're right. You caught one of them. The reconstruction is, I would say, very blurry in certain occasions. Another one is if you, so the decoder currently is a lightweight decoder, the way it's set up. And if you were to replace the decoder or switch the encoder and how many inputs the encoder takes, right, then it's going to be a slower model because now you're feeding it more patches, which means it has to make connections and do cross-validation, do all this for all the patches. And yeah, because it's trained on a low resolution data set, ImageNet, I think, has 254 by 254 images, or like that's the average. It has a pretty low resolution average for their images. So that could be one reason to why it's having all these very blurry images. But that's also a weakness, right? Because we don't have an understanding of how it will perform on a data set with high resolution images. Will this still perform as well as they're saying, or is that the limitation, right? The limitation is the data set that it's trained on, because ideally you should be able to use transfer learning. You should be able to use this for another task, and maybe the task is doing it on high resolution. So I think that's one of the weaknesses personally, is that they haven't really shown much positivity or much about high resolution images. So I'm going to throw this back at you.
Cool. So now we talked about the strengths and the weaknesses. Next thing that we want to talk about is what will be the next step for those researchers to come up with. So the future research could focus on study of a number of patches chosen different mass sampling strategies, which is similar to what David mentioned previously with the different dynamic training time. And also we think they could go with the dynamic and non-fixed number of patches depending on training epochs, where it couldn't be just like 75%, 85%, depending on the size of the original input image. And we have a link to the detailed analysis that was the other researchers read through this MAE, or the Scalable Visual Learners. they wrote another paper that analyzes and more scrutinizing what's missing from those research paper. So you can click on that, the link. We share the same presentation slides on the course presentation course schedule. So you can just click on that, and then you can go into this link and then read more detail about it. So
We have a message in the chat.
papers.
Let me take a step back then.
Okay.
So right here. So to reiterate, they're talking about grid-wise sampling. So the difference between random, block, and grid. Block is the harder of the three to implement. It has a huge training loss compared to the other two. And the reconstruction image is blurry. Whereas grid is easier and it has less training loss compared to block. And they're asking, and it's also sharper. You have more edges in the image, as you can see that you can still see more edges. It's not as blurred out. And they're asking why we think that is the case, that it trains that way. I personally think it's just because it's always going to be the same corners. I think it's just like, it's always taking these patches in a grid style. So there is no way of it, or it's harder for it to fill in the gaps for anything that's, you know, in the second, fourth, every other column and row. It's not really getting this information, right? So I feel like it's harder for it to kind of make that prediction or learn. It's always learning on the same corners, different images and whatnot, but it's just not able to capture the entire semantics of the image. There's not enough diversity in the data set once they do that in a grid style. Whereas in random sampling, you'll get, you know, all sorts of random patches everywhere. So sometimes you will have this data that's capturing certain areas that could represent what you're looking for.
So you can able to reconstruct the neighboring patches and then reconstruct a more higher accuracy from.
That's my opinion, but I'd love to hear, you know,
That's
students
what
and
research paper
professors.
talks about too. That's why it's stated in its research paper too. That's what we think that's the case.
Anyone else has a thought on this and why it might have happened? I like these questions. You guys are having some good questions. Yeah, on our end, we are pretty much done, and I hope you guys enjoyed this presentation. But we're going to leave the next 5 minutes for questions. And the professor, if you have anything to ask and let us know, feel free to.
Yeah, sure.
We
So
have
the
pretty
talk is
much,
very good, right? And also you two collaborated very well for the presentation. Yeah. Any question from the audience?
They're having good comments. Thanks, guys.
Oh, yeah. Any questions?
If not, can we move on to the last slide, David?
My internet's getting a bit choppy.
Oh yeah,
Let me
it's
know.
kind of windy outside.
No question for the talk. Okay, so by the way,
I
I
think
have
they're
one
asking in
question
between.
for the talk. Can we go to the pages? I mean, page 62. I mean, of the slides.
Do you want me to share, David?
Yes, please.
Okay. It says 62.
Yes. So for the reconstruction, right? I mean, if we take a look at the pictures, I mean, for this unmasked, I mean, these regions, it seems in the generation result for this unmasked region, the generation result is very bad, right? I mean, like for the NASTA one, for the grade one, even for some region, we don't do the masking. However, in the generation results, they are all gray. I mean, this region are all gray, right? I think the main problem probably is caused by the loss function definition, right? They define loss function based on these masked regions, right? I think probably they need to incorporate the loss function for this unmasked region as well for define loss function to ensure the generation will be good for both the masked and unmasked regions in the results, right?
So you're saying the loss function,
Yeah,
they
so
fix
if
it or
we look at the
change
gray,
it,
the
that could
gray
potentially
column, right?
improve
No.
it?
Can we go to the previous page? Now,
Sure.
if we look at the gray column, I mean, for some of the region, if we don't do the masking, right, for the unmasked regions, if we check at the generation result, this kind of region, I mean, the generation result, generally they're all gray, right? Even though we know this information as input already. However, in this generation, it is still, I mean, we don't know. I mean, we don't generate this region very well, right? This region, they are the inputs, right? However, in the generation result, they are very bad, right?
Yeah,
Can you hear me?
I agree, Gabe. Saying it, yeah, clarifies things.
Yeah, so this kind of, I mean, this performance probably is under, I mean, expectation, right? We know the information as input already, however, cannot generate them out, right?
Navin's asking if you could repeat it.
Yeah.
In the chat.
So you didn't get it? You didn't get my question, right?
Oh, we got it. Naveen in the chat was mentioning that they couldn't understand it. If you'd like to repeat it. Yeah.
Okay. Yeah, anyway, so any more questions from the audience? Yeah, if we have no question, probably that's it for today. And the talk is very good. And also, I mean, the paper is very interesting. It can trigger many interesting ideas in your mind, and you can incorporate the idea into your projects for some new papers, right? And also for the next class on Wednesday, we will have another paper, right? The next paper is very different from the paper we present in class in these two classes. The next paper is from Jeffrey Hinter. It's a big name. And he will share some ideas with us about his, I mean, new model. It's not a new model, actually. It's a new framework, right? And please also read the paper before class, then we can have a discussion about the paper. The presenter will be Gabriel Simmons, right? So Gabriel, please prepare the slides, before class, and also share the slides to the TA, so we can see the slides before class.
I'll be presenting. Also, just FYI, there's a recording of Jeffrey Hinton himself presenting the same paper on YouTube. So I can send the link to the class. At risk of making myself look bad on Wednesday, you can take a look at that beforehand if you want to get his take on his own work.
Yeah, that's good. That's good. Then we can have both your recording and also the recording for Jeffrey Hinton. Yeah, it's good. Okay. So probably that's it for today's class. And let's also send the speakers. Thank you.
Thank you so much.
Thank you.
So do we stay back or?
I think we have to stay.
Oh, okay. I'm not sure.
The slides are very good. You do, I think before lots of time and efforts to the slide or to the talk. Thanks so much.
Thank you.
Yeah, I think the audience have all left and you're also safe to go.
Okay.
Awesome. Thank you.
Have a great day, Professor.
You too.
Talk to you
Have a nice day. Okay.
Thank you.